by right, I should put a minus sign down here, but I don't want you all to worry about the minus sign, or don't worry about the sign, because once you look at the deformation, you know whether is it positive or negative. Okay, so don't worry about the sign. Okay, so I'll write down here, do not worry. Do not worry about the sign. Okay, I don't want you to worry about sign. So now let's look at the deformation pattern. Okay, so let's say we draw exactly the same now. Okay, let's say we draw exactly like what we have drawn in A. So this is X, this is Y, this is rotation about Z. Okay, so now we draw exactly the same. Okay, now the moment, right, is about the y-axis, and the rotation of the moment will go this way. Okay, so this is the rotation of the vector. Okay, so how I know is that way? So it's right hand rule. Okay, you grab the arrow. Okay, you grab the arrow, not go round the arrow. You grab the arrow where you are. Okay, you grab the arrow where you are. That is our moment. Now, question: can someone tell me how will the structure deform? Anyone?
So the front side will be tensile and the back side will be compression.
I like that. But let's say if you're absolutely right down here. But is this the right view that we are viewing? If we were to view our deformation pattern, how does it look like? Anyone? Do you see smiling face, sad face, or no?
No.
Yeah. Sabah, you are absolutely right. The deformation will look like this. The deformation will look like this. The deformation will look like this. Right? We will just go in and out, yes or no? Right? So, i.e., this is the wrong view. What do I mean by wrong view? If you drew the view correctly, the deformation pattern is either a smiling face or a what? Or a sad face. Yes? We don't see smiling face or sad face down here, do we? So what we have done is we have drawn the wrong view. Okay? So if that's the case, don't analyze from that view, because you can't see whether is it tension or compression, because it's just going shorter, yes or no? So now we view it from a different view now. Okay, so now we're going to view, remember, it's a 3D problem in a 2D world. Paper is 2D. Now this is X, right? Now this is Z now. Okay. Hey, how come my Z don't appear? Hold on. So this is Z now. Okay. Then based on right hand rule, this is rotation about Y. Right? Okay. So I want you to see what I'm drawing now, or where we are viewing. So now when you draw that now, right? Now when we draw that now, how does it look? Okay. So now the look like this. Now the look like this. Oh my God. Okay. Now the look like this. Right? Right? Now this is how it looks. Because why it looks like this now? Because now this is your what? This is your 12 millimeters now. Right? When you drew, when we drew the other way, right? When we drew the other, I'm so not liking Microsoft now. Sometimes it's the user, okay? It's not Microsoft. Right? So where's this dimension over here? This dimension over here. right? This is the 20 millimeters. Okay, and this orange line is shift again. Okay, so now if you view it from this way, right, we know now this is our moment in the y direction, and this is equal to 1660 Newton meter, right? So now when you see it now, we know our deformation pattern will go this way now. Now we see the set face and the smiling face, right? So on this context, I'm going to call this point over here, I'm going to call it my point I. Below here is our point J. Okay, point I and point J. And we know based on the moment vector, this is compression, right? Head of the moment arrow, tail of the moment arrow is known as what? Tensor. We know that now. Okay, right? So that is the analysis. Okay, so now we are again going to apply the formula where stress X is equal to mz or my over Iyy multiplied by z. Okay, so now watch. Now we want to find what? We want to find Iyy, yes or no? Okay. Okay, we want to find Iyy. Okay, we want to find Iyy. So I'm still going to draw the same diagram. Okay, I'm going to draw the same cross-sectional view. Okay, I'm still going to sketch the same cross-sectional view. So the cross-sectional view still look like this. So this is my y, and this is my z, right? So now the region that I'm interested in, or the second moment of area I'm interested now is what? YY. Okay, so this is our axis YY. Right? This is our axis YY. Now, can someone tell me, okay, can someone tell me where is the width and where's the depth? Anyone? Can someone tell me, please?
The width is along y.
Yes. Well done. Okay. I'm just correcting the bloody figure that that Microsoft screwed up for me. Okay. Right. You are absolutely right now. Okay. I'll do that later. So if that is YY, like what you see on the, oh God. Yeah. I'll do that later before I post it online. So what we see now, right? This over here, parallel is going to be the what? Width, right? Perpendicular to the axis is going to be the what? The depth. Right? You can see that, right? So if you see on the right hand side, I do apologize that as I said, Microsoft is doing stupid things to my computer. Okay. So on the left hand side, let's look at the the left hand side. Okay. I'm going to it crashed again. Give me 10 seconds. Okay. I'm going to open my window bigger so there's more wind coming in to cool down my computer. Hold on. Yeah, I'm having a lot of heat issue from my computer today or this week. Hold on. Okay, back to here. Okay. So as you can see down there, right? Like what we have written earlier. Okay, like what we have written earlier. Right, like what we've oh God. It's crashing, it's coming back. Okay. Okay, so let's see what's going on down here. So on the left hand side, like what we've written earlier. Okay, I'm going to erase this because all these are gibberish now. Okay, like what we've diagram got missing. Like what we've written earlier, right? Like what we have written earlier. So we will call this always our width, right? So when it's parallel to the ZZ axis, right? It is the width, right? For this case, it's ZZ because ZZ is our axis of interest, okay? And then if it's perpendicular, right? This will be our depth. So perpendicular to ZZ axis is the depth. Right. So for this case, the one on the right hand side now, right? The axis of interest is the YY, right? So we call this our YY axis. So again, parallel, right? Same thing apply, parallel to YY axis is the width, and perpendicular to the YY axis is the depth. Okay. So like what I told you guys, right? Nothing to do with English at all. All relative to the what? To the axis of interest. I did not know that. Okay, I thought it was English, for crying out loud. Okay, so nothing to do with English. So from here, we know that IYY is equal to 20 multiplied by 12 cubed divided by 12. Okay, so 20 power 3 divided by 12 is equal to 2.88 times 10 to the power 3 millimeter 4, or 2.88 times 10 to the power minus 9 meter to the power 4. Right? Now we can realize that depending on how the moment is acting on, right? I repeat again, depending on how the moment is acting on, right? You have to use the right second moment of area. Yes or no? Right? If you use the wrong second moment of area, that's where the problem comes. As I said, later on, we'll do two axes. Okay, we have moment about the Y and we have the moment about the Z. You have to be able to know how to find the second moment of area. Okay, so from here, all right, from here again, I'm going to call this point. Okay, I'm going to call this point point I. So if we look from if we look at this point over here, based on how I've drawn, so this is my point I. No. So if we view from there, so this is our point I, right? And this is our point J, right? And we know at point I is going to be compression. At point J is going to be in what? Tensile, right? You can why I've written that, because you can relate based on the diagram above, right? Based on this diagram over here, if you look at J, right? J is under tensile, so point J is tensile. Point I is compression, so point I over here is in what? Compression. Okay. So what you see now, okay, if I lower, I want you to compare, okay? So before that, when we look at part A, right, we look at alpha is on top, beta is below. Now I and J, one is on the left hand side, the other one is on the what? Right hand side, right? Okay, so now coming back to here, So now J we know is tensile. So the formula that we're going to use now, we don't need to worry about tensile or compression now. We know where it's going to be tensile, where it's going to be compression. So over here we have stress X of point J, right? So it's equal to my over, so is it my? Yep, my over Iyy multiplied by z. Now another mistake that students tend to make is, what is this z distance? Okay, so if you look at the axis, this is going to be our what? Z distance. Okay, so getting the wrong z distance is not going to help also. Okay, so we know that point J is going to be tensile, so this is going to be plus, so it's going to be 60. The z direction is equal to 0.012 divided by 2. Then divide by Iyy is going to be equal to 2.88 or 2.88 times 10 to the power minus 9. So this will be equal to 60 0.012 divided by 2 to the 2.88 power minus 9 is equal to 125 times 10 to the power 6 Pascal. It's in tensile. And then we also know that stress X at point I is equal to minus my over Iyy multiplied by z. We know it's plus or minus again because we from our analysis, we know that it's going to be in compression. Divided by 2, divided by 2.88 times 10 to the power minus 9. So this is equal to 60 times 0.012 divided by 2 to the 2.88 power minus 9. So this is equal to compression minus 125 times 10 to the power 6 Pascal. Okay, so what I propose now that we go for a break. Okay, so now it is, we come back at we come back at 11:50. Sorry, not 11:50. What do we do? We come back at 10:50. Okay, so I'm going to shut down my computer, let it cool down, and then we come back at 10:50. Okay, so go for a break. Thank you.